So did I pronounce your name okay, or Yusuf?
Yes, Yusuf Sulistya Anugraha.
Okay, Yusuf. Okay. So I'm gonna. Can you share your slide? Hello, everyone. Welcome to the session. It's version control and then programming. So my name is Sung Kim, and then I'll be the session chair of this wonderful session. We do have 6 wonderful talks, and then also we have very, very good presenters. The first talk is about the fixing upstream merge, and then Chung Ha from USC will talk about it. Let's welcome our first speaker.
Thank you for the instruction. For the screen. So can you see the screen?
Yes.
Okay, let's get started. Hello everyone. My name is Chong Ha Song from USC, working with Cha Wang. And I'm going to present a study of upstream-induced merge conflicts and its fixes in divergent forks. This is joint work with Shivendu, Mike, and Pallavi from Microsoft. A divergent fork is created by a fork, and it is widely used for customization and independent development by saving a lot of effort without starting a project from scratch. For example, Android OS is customized by different device vendors. In divergent forks, we call upstream for an original project and downstream for a project created by a fork. One of the most popular examples is a Chromium-based web browser. There are many web browsers forked from Chromium. To understand divergent forks, we use data from Microsoft Edge development process, but we do believe this study will help to understand the nature of divergent forks. Then what is the problem of these divergent forks? Since they are forked from original projects, we need to regularly merge the changes from upstream for important updates, such as security patches and feature changes for compatibility. However, the problem is this merge causes conflicts like build breaks or test fails. Let me use a simple example with a commit of Microsoft Edge. Let's say Edge is released in April, and after some time during May, the Edge team noticed Chromium made some security updates. So the team tries to pull the changes by a merge from the recent Chromium. And during this merge, we encounter a build break because of the changes from the upstream. It says a function call of selected index is an undefined symbol in this file. Then an engineer tries to figure out the problem by looking at Chromium's commit history. As the source code cannot be built, it usually takes from several minutes to hours, depending on situations. Finally, the engineer finds the function definition of selected index has been changed to get selected index in a commit history, and a corresponding function call change. So the engineer updates the Edge code accordingly. And this kind of fix happens several times more to actually build the code. Based on our data, there are more than 25,000 commits made in Chromium for 3 months. And it is necessary to merge since it may have important updates. But it consumes a lot of engineering work when upstream code frequently updates like Chromium. Due to the reasons, we found out many Chromium-based web browsers are behind around 1 to 8 versions from the recent Chromium. So what is the ideal way to save this cost? Here is what we think. First, we have a build break on a specific file, and we provide a magical autofix feature. And by clicking this button, it automatically updates the code. Also, it provides the root cause of the build break. Then everyone will be happy as we save a lot of engineering cost. But is this even possible? To answer this, our work has 2 contributions. First, we understand the nature of merge-related conflicts in divergent forks by studying them. Second, we provide a prototype tool for fixing the merge-induced build breaks with an AST-based auto patch and input commit pruning. Finally, we check the feasibility of this tool by applying it for real conflicts. Here is an overview of the simplified structure of the Edge development process. The dashed lines show branches from top to bottom: upstream, integration, stabilization, and downstream branch. And each dot shows a commit made by each branch. This red dashed box shows what happens every merge. There are two branches involved during this merge: integration branch and stabilization branch. All merge-induced conflicts are resolved in these two branches. And finally, the buildable version is merged back to downstream. Here's the distribution of fixes we studied from stabilization branch and integration branch. It has three categories: texture conflicts, build breaks, and test fails. Among these, we target build breaks for automatic patches. The reason is the build breaks cost a lot of effort of engineers, as they need to look up the history of upstream changes. And we further categorize the types of build breaks based on causes and fixes. Based on the study, we provide an automatic patch procedure as shown in this figure. First, I'm going to talk about AST-based automatic patches. The procedure is from two versions of files of upstream. We diff the ASTs of them and infer possible patches. Then we apply the patches to downstream files. We infer patches by checking definition changes and use changes between two ASTs. For example, here, AST diffs the two ASTs and shows the definition of the function name is changed from selected index to get selected index. This shows a use case change where the same name is updated under function call node. Finally, we infer this patch since we have a consistent definition and use changes. With this inferred patch, we apply it to downstream. We search if there is any match in this AST. And we find there is a call with the name selected index, so we apply this change on this node. This AST-based approach seems reasonable, but we have a scalability issue when we just use this approach. As the size of the source code is really large, creating ASTs and diffing ASTs for all files are too expensive, and there are too many commits to consider. So we need to prune the input commits for this AST-based approach. Here is a diagram to describe input commit pruning. Let's say we want to fix a build rec here. Since we are not able to build the source code here, we find the latest compiled version from this point. And this is the latest working version. This version doesn't have change information after we merge. So it has original connection of the symbol name, which was not resolved in the build rec point. Then we use a symbol table of this working version to track the definition of the broken symbol and the file name that has this definition. Next, with the file name we find, we search which commit actually modified this file through this upstream range. This upstream range is between the last commit we merged and the commit we want to merge. In this range, we get specific commits that are responsible for this build rec. Therefore, we effectively reduce the upstream files to consider for this AST-based approach. With this framework, we check the feasibility. On average, our framework could fix almost 40% of the considered commits, and each fix took around 70 seconds, which is much faster than human-driven fix. Also, input commit pruning could reduce the number of commits to consider by 3 orders of magnitude. Here is the conclusion. Our study shows the first industrial case study with Microsoft Edge data to understand the nature of merge-induced conflicts in divergent forks. Based on our study, we categorized the conflicts and provided an automatic patch method for build recs. And our results show this encouraging feasibility by providing an insight into divergent fork development. Thank you for listening to this talk, and please find our paper for more details. And I'm happy to answer any questions.
Yeah, thanks a lot for the great talk. Any questions? So this is very, very impressive. So my question here is that the 40% you can fix automatically, right? But those like conflict, how easy or how hard to fix for human?
We didn't actually measure each fix by human driven thing, but on average, it took like 30 minutes to read even for the simple fixes, if the engineer is not familiar with the code.
Oh, okay. So definitely it's useful to use this tool, right? One question from the audience, it asks that is that possible that the integrator performed additional changes after that merge? And those changes were responsible for the broken build, for example?
Could you repeat the question? Because
Right. So is it possible that integrator can add additional changes during this merge, automatic merge?
integrator,
Yeah,
does it mean the human or
human. I think. Yeah, I think.
yeah. So right now the entire process is not for providing complete set of patches right now, but it's more like a recommendation patches, and people can apply if they want, and some of the patches may not be applicable. So yeah, integrator will get involved during this process.
Okay, so that's great. Let's thank our speaker one more time. Thank you very much.
Thank you.
And then our second talk will be something about information for aging perspective. And Sruti from Microsoft will present the second talk. Okay, do you want to turn on the microphone? Yes, thank you. Yeah, let's welcome our second speaker then. Yeah, go ahead.
Thank you, Sankim. Hi, I'm Shruti Srinivas Raghavan. I'm a postdoc at Microsoft Research, and I'll talk about version controls from a slightly different perspective today. So here's the problem. Developers seek all kinds of information from their version control repositories, and a prior work showed that they face various difficulties when they actually have to find something there. And here we explore whether information foraging theory can help understand and mitigate some of these difficulties. Now, we chose information foraging theory because it's a theory about information seeking, right on the spot of our problem, and it's been successfully applied to very practical tool design for environments from web search engines to programming IDEs and to program comprehension tools. And so we think it'll similarly help version control. And in a minute, we'll see what we found. So what is this information foraging theory? Information foraging theory, or I'll call it IFT, basically says that people's information seeking is very similar to how animals forage for their food in the wild. It predicts as well as explains information seeking behaviors. So in IFT parlance, a software developer is basically a predator looking for information prey in their version control environment. And the prey might be hiding in one or more locations called patches, such as commits or diffs. And a predator goes from one patch to another via various links, including by scrolling to get to their prey. So how does the predator find the prey? IFT says they do so by sniffing various cues in the environment and using the scent. An example of cue in a version control is like words in commit messages or the reds and green colors, right? A predator sniffs those and decides which way to go. Now, this scent following is basically at its core an optimization strategy. IFT says that a predator wants to maximize the amount of valuable information gained for the cost spent gaining that information. And the scent is just basically a way of estimating these costs and values in a predator's head. So we took this theory and these constructs, and we used it to analyze data on how people seek information in version control. This was the data we gathered in our prior work, and it came from 14 interviews and a larger survey, and we reanalyzed it with an IFT code set. Here's what we found. We found that participants engaged in 3 distinct kinds of foraging-related activities. I'll go to the details in a minute, but then across all 3 activities, the core of what developers thought about was costs and values, and they always wanted to optimize that ratio. So the core of IFT applies across the board. But then they also applied in slightly different ways. So in the case of foraging for specific information, participants were looking for things like when was this bug introduced, or why is this code implemented this way, so that they can go and complete a task. So in this case, they were interested in very specific information, and so the value is fixed. So the optimization problem they solved is, how can I get this information in as least cost as possible? This kind of foraging has been studied extensively in years of prior IFT work. And the good thing is then we can take all those design insights and apply them directly to design some of design environments for these activities. Turns out a lot of the barriers that developers reported actually fell into these categories, and the paper has very concrete design recommendations for how we could get over those barriers. And this includes improvements to existing tools as well as opportunity for new tools. I encourage people to look at the paper. The second kind of foraging was foraging for change awareness. Now, this one was slightly different from the previous one. So here, participants did not have to go and find anything. Instead, all recent commits were actually easily available. You could just do a git pull and get them all. Now, what participants actually had to do was to go over them, decide which ones were important, and actually consume them in a very lightweight manner. And by lightweight, we mean at a very low cost, not spending too much time sweating over the details. Here's an example of how that looked. So this participant described it as, each commit sends you an email, so I just scan the subject lines and I can kind of see which direction the code base is going. It's not about the details, it's more lightweight. Now, IFT actually acknowledges this kind of lightweight foraging, where a person has to get just the high value information at an overall low cost, but it's not been concretely applied in concrete situations. And so we have an opportunity for researchers to operationalize this lightweight foraging in the context of change awareness, and that way advance both IFT as well as change awareness tools. There's also another opportunity for tools to support change awareness when people have to catch up with a whole bunch of changes. And this happens all the time with large projects and when people say come back from a day's vacation. I won't get into the details, but the cost value considerations for such tools is discussed in detail in the paper. And then comes the third activity, creating commits. So when creating commits, participants were not thinking about their current task, but they were thinking about how can I create commits and commit messages in ways that will make my future foraging easier, such as bring down the cost. For example, almost all developers thought about writing good commits and commit messages so that it's going to be easier in the future. But they couldn't always satisfy those future foraging needs because they had to deal with various kinds of tensions. Here's an example of how those tensions looked. So this participant said, I prefer small commits. It captures history better, it makes it easier to prune out changes, but then it's hard to see what dependency exists across commits. So what is good for one kind of task is actually not so good for another kind of task. So pulling down costs in one place actually pulls it up in another place. And that's a tension participants struggle to balance. Here's another example. So this participant's team had rules such as you have to have all your tests running when you commit. But that kind of came in the way of this participant actually progressing with his current task because he had to share something. So here the tension is between current task progress versus optimizing things for the future. Now, these tensions are, of course, not easy to balance, but we do have to start thinking about how we can balance them. Here are 2 possible research opportunities going forward in trying to balance these tensions. One is on the consumer side, where we say different foraging activities means people require different kinds and different levels of information. And we need to start thinking about tools to support all these various kinds of activities with very different requirements and often conflicting requirements. And then on the producer side, we need to start thinking about how do we better enable people creating information. And that really affects how foraging happens eventually. And so we need to start thinking about tools to enable people commit changes and write commit messages. Here, classic IFT doesn't offer much, but a variant called social IFT does help. And it's acknowledged these tensions and offers things like what's an ideal commit size? So what's an ideal team size? So we could draw from those models to try and understand some of these tensions to build better tools. And that brings me to the end of the talk.
All right, that's wonderful. Do you have any questions? Let's see. So this is a very interesting idea. So how did you actually come up with this new concept called ITF from the first place?
So information foraging theory is a very popular theory in the HCI world, and it's fundamentally about how people seek information. And software engineering has a history of applying these to things like requirements engineering and IDE design, but it's not been looked at in the context of version control. So we actually started off trying to understand how can we improve version control tools, and we found that there is a big set of information related problems there that we had not looked at before. And so we said, okay, now that we've seen it, how do we analyze this data? And then, we looked at the literature and brought this theory for that. Turns out I also had a committee member in that space, and it kind of came together.
Okay, that's good. Do you have any question from audience? Okay, then let's thank our speaker one more time. Thank you very much.
Thank you.
And then our next talk is also very interesting. It's about different diff algorithms, and Aesop from the NARA Institute of Science and Technology will give us talk. Let's welcome our third speaker.
Okay, first let me share my screen. Okay, can you see my screen now?
Not yet. Can you try one more time?
Okay.
Wonderful. Go ahead.
Okay. Okay, now you can see the share screen.
Yes, go ahead.
Okay, thank you. Hello, everyone. I'm Yusuf Sulistyo Nugroho from NARA Institute of Science and Technology, Japan. In this opportunity, I would like to present my journal paper entitled How Different Are Different Diff Algorithms in Git. In empirical software engineering research, diff is commonly used in various topics. Along with the growth of GitHub, recent studies analyze software changes extracted from Git repositories by using the Git command. For example, the Git diff. But do you know that according to Git documentation, Git offers diff utility for users to select the diff algorithms, either Myers, minimal, patience, or histogram. In textual differencing, all diff algorithms are computationally correct in generating the diff outputs. Without specifying the algorithm in git diff command, Myers is used as the default diff algorithm. Although histogram that was introduced in Git 1.7.7 in 2011 might give better performance to Git diff, it is not popular among software engineering communities. The result of previous studies might be different since then if they consider histogram in Git diff command. Thus, in this study, I only focus on comparing the differences between Myers and histogram. However, the diff outputs are sometimes different due to different diff algorithms. Different diff algorithms might identify different change hunks, that is, a list of program statements deleted or added contiguously separated by at least one line of unchanged context. The figures illustrate two diff outputs extracted using two diff algorithms, that is, Myers and histogram. As we can see in the example, there are two differences: the number of the change lines and the position of the change lines. In Myers diff output, we see 9 added lines of code from line 5 to 12 plus line 16, and 2 deleted lines of code between line 18 and 19. While the histogram diff output, we see 4 deleted lines of code from line 5 to 8 and 9 added lines of code at line 9 and from line 13 to 20. To clarify the impact of adapting different diff algorithms on empirical studies and investigate which diff algorithm can provide better diff results that can be expected to recover the changing operations, we carry out 2 sequential analyses, systematic mapping study, and empirical comparisons. For the systematic mapping, we collected papers from 3 top journals and 8 high-ranking international conference proceedings that were published from 2013 to 2017. Out of 3,000 surveyed papers, mapped 52 selected papers to understand which diff algorithm is used in previous studies and the purpose of mining Git repositories. The results reveal that all collected papers had never considered the other advanced diff algorithms. We also found that the purposes of using the git command were to get patches, followed by matrix collection, and bug introducing identification using SZZ algorithm. Based on these top 3 popular usages of git diff in previous studies, we conducted an empirical analysis to compare the diff outputs generated by 2 popular diff algorithms that are Myers and histogram. We then applied these 2 algorithms in 3 applications based on the usage of git diff, collecting metrics, and identifying bug introducing change using SZZ algorithm, and manual comparison on patches. The results show that the percentage of files having a different location of identified change lines of code are 4.17% and 4.62% on average in the application of matrix and SZZ algorithm respectively. Considering commits, we found that the different location of the change lines of code accounting for 7.79% in matrix and 9.68% in SZZ application averagely. The result of our manual investigation on patches shows that histogram algorithm provides better outputs compared with the Myers in describing the code changes from source code files. But they have almost the same ability to extract the diff from the non-code changes. For example, the changes of a text file. To sum up, our quantitative analysis have shown that different diff algorithms can report different amount of change lines and identify different change location. Our qualitative investigation reveals that histogram is better for describing code changes. Since diff is the fundamental tool for various software engineering tasks, considering the limitations and advantages of algorithms is important. Thus, currently, we recommend using the histogram algorithm when analyzing code changes. So I'm happy to announce that this journal paper has attracted people to discuss in Hacker News. And also this publication has been referenced in Wikipedia for describing the diff. Our study has also been referenced to the actual tools. First, it was shared and discussed in Git extension. And the second, it has been implemented in PyDriller. So now the PyDriller users can consider histogram algorithm in their experiments. So that's all I have for my presentations, and you are very welcome to read my journal paper and check it for more details. Thank you for listening.
Wow, this is very nice and very interesting that have a Git extensions and other tools. It's wonderful. Do we have any question about this?
A quick question. Sorry.
Sure.
Hello.
Go ahead.
Can you hear me?
Yeah,
Okay.
Yes,
go
yes.
ahead.
So my question is, in your paper, do you have any guides for different mining tasks for maybe which diff mode is more suitable for like different categories of mining tasks, or you always recommend one specific diff mode for every mining task?
Sorry, I don't get your question.
Repeat one more time.
Okay, so my question is, are you always recommend one diff mode in be used in the mining tasks, or if you provide any guides for different mining tasks?
Okay, so currently we don't provide any guidelines to mining any code changes, but based on our study that shows that histogram is much more better than the Myers. So just we can say that currently histogram is better for describing the code changes instead of Myers, while both algorithms are better in extracting the non-code changes. For example, if you extract the text file or source code to extract the changes of code commands, so you can use both algorithms, either Myers or histogram. But if you want to find out the differences of or the change of the code, then it is better to use histogram.
Great. So actually, there are many questions here. Hopefully, we can get the. Hopefully, you have time to answer these ones after this session, maybe in the Slack channel or QA. But there's one very interesting question here, so we can just do only this one, and then we can finish this session. This talk. So, do the different diff algorithms can impact to the occurrence of merge conflict? Which means that if you have different diff algorithms, do you think the merge conflicts will be different as well?
Okay, let me. So currently we do not study on that case. Maybe it is also better for us for future research to apply this diff for the investigation of that merge conflict. So we cannot say that currently the diff is have differences on the merge conflict.
Okay, thank you very much. Let's thank our speaker one more time. Thank you very much.
You.
And then we're gonna move on to the next talk, which is about the impact of Java annotations in practice. And Zhong Shen from KTH Royal Institute of Technology will give us talk. Let's welcome our speaker, Zhong Shen. Okay, looks good. Go ahead. So I think it's a little bit difficult to hear.
There's no sound.
No sounds. So can you try one more time, Chongqing? Otherwise, we have to play the videos instead. Okay, so I think Jumar, can you play the videos instead?
Okay, Professor, we are having some technical problem with the video. Can we skip to the next presentation and then we will try to make.
Okay, that's good. So we will come back to this Java annotations, and then Chongqing, can you unshare the screen? Okay, so we're gonna move on to the next talk. Also, it's a very, very interesting title, Why We're Reinventing the Wheels. And then the Bowen from Singapore Management University will give us talk about this. Let's welcome our speaker, Bowen. And then,
Okay, so
yeah,
I'm gonna share my screen, right?
Yeah, can you try to share it?
I cannot start to share my screen because the host.
Okay, here we are.
Okay. How about now?
Wonderful.
Can you? Okay, so let me start. Hi, welcome to my talk. My name is Bowen from Singapore Management University. Hold on. Okay, so the topic of my presentation is mainly about code reuse. And in this work, we focus on the code, particularly in library level, with two concrete and opposite scenarios. The first scenario is called library reuse, means that developers replacing self-implemented code with an external library. Although it is common, reuse decisions are not frequently revisited, and there is no clear evidence that the decisions are always quality-driven in the literature. The second scenario is code re-implementation, that developers replacing an imported external library with self-implemented code. Although code re-implementation is less common than library reuse, libraries were not always reused by developers, and developers sometimes still choose to re-implement the behavior of an existing library. And we found that the reason about why developers re-implement code instead of using external library haven't been investigated in the literature. To fill the gap, we proposed 3 research questions to investigate the rationale behind the 2 scenarios. The first and the second research questions are mainly answer the reasons behind library reuse and the re-implementation. And the third research question is about under what circumstances do developers prefer to reuse or re-implement code. So first, I'd like to briefly introduce the overall design of our study. In summary, we focus on 2 program languages, Java and Python, and collect our experimental data in 3 ways. First, we designed an open survey to collect the opinions of developers for both library reuse and re-implementation through online communities, developers in IT companies, and software engineering researchers. Second, we also propose an approach to collect real-world cases from open source projects in FDOR, GitHub, and existing work. The approach is based on an assumption that if a pair of removed and added method invocation is located close to each other, then they are more likely to be library reuse or re-implementation. So that's why we introduced the concept of relative distance to filter unrelated code changes. And then we manually identify each of the remaining code changes to see whether it belongs to library reuse or re-implementation or neither. So for the identified cases of library reuse and re-implementation, we send an individual survey with the concrete code changes to the corresponding developers. So in a sense that the individual survey is customized. And for the last mean, we also manually analyze commit messages, as we found that developers also mention a reason in the commit messages sometimes. Due to the time limitation, here I only choose to present the answers of the third research questions, which is related to both library reuse and re-implementation. And we found that the findings derived from two different programming languages are similar. In summary, nearly half of the participants prefer to reuse an existing code in any cases. However, they also want to make their own implementations if they need a higher code flexibility, or they cannot find any libraries that satisfy their requirement, or the libraries is not light or simple enough. According to the results, we derived several findings, and here I choose to present two of them and their implications on how the existing library recommendation techniques or even code recommendation techniques can do better in the future. The first finding is about what kind of information that developers want to know for their decision making. For example, whether the recommended library is developed by a team with high reputation or it is well documented, and so on. From this perspective, displayed libraries characteristics can help developers to quickly assess the quality of a library. Also, the recommendation tool can group similar library for developers to compare and select the library they prefer. In such a group, recommendation tool can further rank the library based on the numbers of users, reviews, and documentation quality. The second finding is about sometimes developers need warning more than recommendation. If an imported library is deprecated or badly rated or inactively maintained, a library recommendation tool may want to suggest the developers to replace the library with an alternative library. So to do that, the recommendation tool can collect the information from the libraries, for example, library website, and provide useful warnings. Okay, that's pretty much I have for my presentation, and you are very welcome to read our paper and check out more interesting points. Thanks.
Okay, thank you very much. Any questions from the audience? So I really liked your implications, especially the second part that if the developers, yeah, exactly. So they want to re-implement it, we're gonna give them warnings. Did you actually have any chance to check that if this is really the case, which means that you had an interview, right? And then we can ask that if you knew the libraries existed already, maybe did you reuse it or implement it? Did you check on that point?
So currently we derive the funding and the implication from the survey, mainly from survey and the commit message. But I think you mentioned a very good point that maybe we can interview them to know more about why sometimes they need negative recommendations. And maybe, yes, I think it could be a very good future work to interview them and know more about or have a deeper understanding about this recommendation. Yes.
Yeah, so yeah, wonderful. Thank you very much. Let's thank our speaker one more time.
Thank you.
And then we're gonna move on to the next talk. which is also very interesting. It's a heterorefactor. Jason and Quen from UCLA will present this exciting idea.
Thank you. Here we introduce heterorefactor, a framework that posts programs into accelerators in one click instead of weeks. I am Jason Lau from UCLA, advised by Professor Jason Kong.
I'm Qian Zhang from UCLA, advised by Professor Myung Kim.
Jason Ashwaya and Chen are co-first authors, and this project is a collaboration between Professor Kim's software engineering group and Professor Kong's group on hardware and architecture. Large-scale software systems require high performance and energy efficiency. To achieve these targets, heterogeneous computing are used to port computation-intensive parts into accelerators. FPGA is a device whose circuit can be reconfigured as an accelerator. It often exceeds the performance of CPUs by several orders of magnitude, and at the same time uses less energy. But why isn't everyone using FPGAs if they are just awesome? The answer is they are extremely hard to program. The use of FPGAs is limited to their hardware experts and requires weeks to months to program. 10 years ago, people have to write programs in hardware description language such as Verilog to use FPGAs. This language is pretty much assembly. There are no types but bits and instructions. There are no control flows but go-to statements everywhere. They made writing FPGA programs a nightmare. The good news is recent advances in high-level synthesis compilers liberate the developers. With high-level synthesis, you can now write an accelerator using a programming language that is similar to C++ without worrying about the low-level details, and that will be synthesized into hardware. However, we still observe significant gaps for software programmers. For example, even the largest FPGA nowadays only has tens of megabytes of memory. Therefore, developers need to optimize the bit width to save space, which depends on the input. Traditionally, they allocate integers with a fixed size bit width large enough for all possible input values, which wastes memory. Likewise, they need to tune the precision of floating point numbers to trade off between precision loss and memory. Besides, the FPGA tools do not support recursive data structures. Therefore, if you ever attempted to port a real software code to run on FPGAs, you will be frustrated to see a lot of errors. For example, in a simple binary tree, there will be 4 compilation errors. Nested pointers are not supported. Dynamic memory management is not available either. So user should pre-allocate fixed-sized spaces by over-approximating the input. The types of allowed pointers operations are restricted, and all your recursion functions will not compile. After 30 years of evolution, we are surprised to see that even a C program written in 1989 cannot directly run on an FPGA. The developers have to manually rewrite the programs, which is a lot of hassle and can cause errors. They also have to over-approximate the bit width of integers, the precision of floating point numbers, and the sizes of dynamic data structures. This causes waste in the scarce on-chip memory. It's time for the software engineering community to lower the barrier for FPGA development. We had a dream. We had a dream that one day every programmer can just compile a software code for FPGAs. We had a dream that no one should worry about wasting the memory. We had a dream where there are no gaps between software developers and FPGA acceleration. We want to realize the dream where there is a tool to understand the code and refactor it.
Thank you, Jason. We proposed a new dynamic invariant analysis and automated refactoring technique called heterorefactor. It instruments the program to monitor FPGA-specific dynamic invariants, for example, the size of recursive data structures. Using this kind of knowledge, it automatically transforms the program to the runnable version with optimized bit width, and it selectively offloads the computation from CPU to FPGA only if an input falls within the dynamic invariant. Okay, here we go. Our first task is to make the original unsynthesizable recursive data structures synthesizable on FPGA. In the instrumentation step, we get the data structure size and the recursion depth using a set of typical data. Based on the collected invariants, we use the rules compiler framework to perform code refactoring based on these 3 refactoring rules. This is an example recursive binary tree program. To rewrite the dynamic memory management, we pre-allocate an array with the monitored size. We replace the malloc and the free with our implemented node malloc and node free, which returns the index of an array, and we replace the tab of return pointers to the offset of elements in the array. These tab changes are propagated to the entire program. Then we change the pointer accesses to array accesses using the offset value. Finally, we transform recursions into iterations based on the stack. Okay, in addition to make it run on FPGA, resource efficiency is another important concern. Traditional FPGA design requires a programmer to define the bit width for their variables. Hito refactor automatically finds the minimum bit width for integers and floating points. For integers, we first monitor the FPGA-specific dynamic invariants, like their value range, by canvas-based instrumentation. Based on the observed data range, we modify the integer tab with custom bit width to represent its max value. For the floating point tuning, we design a probabilistic differential execution-based approach. It first generates program variants with different precisions by source-to-source transformation. For example, we use rules compiler to get 2 transformed versions, one with reduced precision and another one with original precision. After getting these variants, we measure the precision loss using differential execution. We add a verification function to check whether the error is within the threshold or not. We call this one sample of verification. So apparently, one sample is not sufficiently reliable. Therefore, we use Hofstad's inequality to calculate the minimum number of required samples to achieve our confidence level probability. With reduced bit width and data structure sizes, we may have input that validates an invariant at runtime. To ensure correctness, we add an input check on the host and an immediate check on device. Whenever the error happens, the host will restart the computation on CPU. Okay, from our evaluation, Hito refactor automatically transforms the original unsynthesizable code to the synthesizable version with no human effort required. And automated refactoring can reduce the human effort by 49% if we compare the manual code with the original code. In addition to make it run automatically, we also demonstrate the efficiency of our resource optimization. For different types of kernels, we achieve significant resource reduction of about 50% and increase the maximum frequency for some cases. The resource reduction will in turn lead to higher parallelism and performance. Thank you for all support of this work. To sum up, we adapt the automated refactoring to heterogeneous computing with FPGA, and this combined dynamic invariant analysis and the automated refactoring technique is unique to the best of our knowledge. Thank you.
This is very, very nice. Do we have any questions from audience here? Slido. Yeah. So my question is that this is really great, right? But how can you really verify after you do refactoring? So I saw that there is one kind of module that you're saying probabilistic verification, but how good it is?
For the you mean the floating point verification?
Mm-hmm. And then everything. Basically, if you do automatic refactoring, so we need to make sure that the refactored code is correct, right?
Yeah. Okay, so to guarantee the correctness, to guarantee the correctness for the refactored program, we did the differential execution between the CPU function and the IPG kernel function, and compare the differences between these 2 versions. But for the floating point, we call this one sample of verification. We call this one verification coded as one sample. So apparently, one sample of verification is not reliable enough. So we want to achieve the objective, that is the probability of the error is within the threshold is larger than confidence level. So we use Hopkins inequality to calculate the number of samples to achieve that objective. That is to say, so one sample is not reliable, but after running it for n samples or n times, we will achieve that objective with at least our predefined confidence level.
I see. So this tool is great. So can we download and use it from today? Or?
Yes.
Wonderful.
Yeah, it is open source, and yeah, it is very easy to use. Just one click, you will get a IPG synthesizable version for your C program.
Okay, so that's great. So wonderful. Let's thank our speakers one more time. Thank you very much.
Thank you.
Okay, so our last talk, Jongshin, we had some technical problems before. Do you think you can try to present one more time? Jongshin?
Yes, Professor.
Let's try one more time, and then if it works, we can go. Go ahead.
Okay, I'm sorry for the
It's
issue.
okay. Yeah. Can you share the screen?
Yes, I'm trying.
Yeah, your sounds good. So let's keep our fingers crossed at this time.
Can you see my slide, Professor? Hello?
Not yet. Try one more time and try harder and see how it goes. Oh, I saw something blinking. So one more time. Great, something is happening. So I think there is some technical problem. So let's see, Zhongxing, are you trying right now, or how is it going? Right. So we really excited about your work, but unfortunately, due to some technical issues, unfortunately, we cannot have you at this point. But what we're gonna do is that we're gonna get the videos from you, and then we're gonna post your videos along with the discussion video in our XC webpage. So later, people can watch this talk, and then if you have any questions, we can further discuss on your work on the annotations, right? So that's what we're gonna do. And then this actually basically concludes our session. And once again, thanks a lot for joining this session. Thank you very much for the wonderful presentations. Thank you.
Thank you, Professor.